Last time on ENGR 315-A, we talked about thin wall pressure vessels, but kind of wrapped up the conversation talking about a 3D form of Moore's circle. So we're going to run through just a example of using it today, and I would love to get into a last quick thing on buckling, but as we were just talking about, this is it for mechanics and materials. Try not to cry. I know that this brings you great sorrow. However, on Wednesday, if you have questions that you would like to go over prior to the final, which is presently scheduled for Saturday from 8 to 11 a.m., please let me know, and I'll be prepared to go over stuff on Wednesday on topics that you specifically want to see examples of. If, as said, if you would like to not do the final exam from 8 to 11 a.m., I'm fine with it, but the entire class has to agree on the time to move it to. So it's up to you guys to figure it out, like at a different point in time. Again, the entire class must be in agreement right now and for 8 a.m. May 2nd. All right. For the format would be similar to the last test. And as Nick had just asked, yes, the test will be cumulative because everything in this class is cumulative. So expect to see at least we'll expect to see a torsion thing on there, bending thing, more circle things, all sort of stuff. All right, so let's get it on. Popping over to the dock camera. All right. Going to have ourselves a look at a pressure vessel. So do like a side view, front view sort of thing. So outer diameter, 12.6 inches. Wall thickness, 0.11 inches. Has some internal pressure in 210 PIG. All right, so I want to find the maximum stress in the tank, assuming that it's going to fail due to shear stress. So how do I start off? How do I find stresses in this tank? Sorry, I'm drawing small again. How do I find stresses in this tank?
You're going to cut a section long ways and then the other way too.
Like that, and then I'm blanking, and then kind of a section like this as well.
Yeah.
Okay, cool. So let's see if I can draw. So here's my section. I've eviscerated a chunk of the tank. As well as some of the pressurized fluid that's in it. Try to shade things into what they are. And so that's my that T, it's my 0.11 inches, and then add a outer diameter marked over here. Let's call it OD equals 0.6 inches. Okay, what now? How do we find here before?
Can we just use the equation for stress that we determined last time, or should we sum the forces?
So here's the fun thing with thin pressure vessels. Unlike everything else that we've played with, they're actually really easy because it's the same game every time because of the assumptions that we've made. It's always going to look like this. There's always going to be some pressure here, and the pressure is always going to be pointing in the same direction. So pressure is fluid, so it's always pushing outwards and all that. And the wall's always thin, because else it wouldn't be a thin wall vessel. So really, we actually don't have to cut any sections, so long as we identify that it's a thin wall pressure vessel. How do we identify that? Confirm that this is a thin wall pressure vessel? What was with that assumption? What was the condition of the thin wall assumption?
Wall thickness at least.
The radius is 10 times bigger than the thickness.
Right. So in order to be a thin wall pressure vessel, we said that has to be true. So, is it true? So we're given an outer diameter. We call all of our computations were based on what radius? The inner radius or the outer radius? So those who were in it, so who are interested, all of our computations based on inner radius of the pressure vessel. In this case, we aren't given the inner radius. We're given the outer diameter. So if we do a little bit of geometry, we can find that the diameter is like 12.38 inches. We consider radius is 6.39. So I'll call my radius RI, 6.39 inches. Our thickness, we already said, is 0.11 inches. In order for the thin wall approximations to hold, the ratio of inner radius to thickness to wall has to be greater than 10. In this case, Ri over T is approximately 56.2. Sorry, 0.3. So our thin wall assumption valid here. We use it. Okay. So if the thin wall assumption is valid here, then that means that we can just grab equations from last time and throw and say, hey, here are my stresses. Because as I said, all these pressure vessels, we assumed that they all take the same shape. They're all cylinders with spherical ends. We just said thin walls, we can throw this thumb in. This has a thin wall on it, so we're good to go. So we assume it's axisymmetric geometry, assumed uniform internal pressure. So if we assume these things, we can just equations and chuck them at it. So can I move? So you guys all got it? Sounds gives a sense. So yeah, Annabelle, just like you were, we don't necessarily need to do a free body diagram in this particular case because we've assumed so much about the geometry and the problem that all that we need to solve this problem are literally the inner radius. We said is 0.39 inches. The walls, which we said is 0.11 inches, so this is part of the problem, and the pressure, which was 210 psig. Question: pressure. Do we need to worry about like atmospheric pressure pressing back at the cylinder? Is that going to be accounted for in this problem? It's called to account for the pressure outside of the pressure vessel, stuff that's pressing back on it. And if you're not sure what I'm asking, just we'll talk about it because it'll show up now or later. So the reason why this is all the information that we need is because of how the pressure has been given to us. So given as PSIG or PSI gauge. So what's different between gauge and absolute pressure? If I stick a pressure gauge outside right now, it'll tell me that it's 14.7 psi or 1 atmosphere. But here's 14.7 psi or 1 atmosphere. This is an absolute pressure. It measures relative to a vacuum. So I'm 1 atmosphere of a vacuum. If the pressure was 0 atmospheres, there'd be no air, no nothing outside. It would be a vacuum. If it's absolute pressure. So you usually say as PSI or PSI A. PSI absolute. Pressure measures a pressure relative to something else. In this case, it's usually the outside of the tank. So when you see a PSIG with reference to pressure vessels, it's measuring whatever the pressure is inside the tank in terms of absolute pressure minus the pressure outside the tank. So when I ask whether or not this takes into account the pressure outside of the tank, it's done that. So you don't need any other information. You don't need to do anything else to this number. So this really is. I'm just going to cross this out because it's not what we're using. So these 3 bits of information really are all you need in order to find pressure in the stress in a thin wall pressure vessel. We know that if we back to here, if we call this direction my X direction, call this direction my Y direction. Okay, so longitudinal direction is X, say, and the lateral direction is Y. Then I can just plug into those equations. Say sigma X equals 1 Pn Ri over 2T, and crunch those values. I get something that looks like, let's say, 10 PSIG, 6.39, that 2.11, something that looks an awful lot like 6.1 KSI. And I can do the same thing for sigma Y, which I think is PR over T. Oh, 12 to KSI. And we said before there is what you call on the sections that I've cut, all the relevant sections for the for a thin wall pressure vessel, there are no shearing forces. Therefore, there are no shearing stresses on either of these sections. There are only normal stresses, which is awfully convenient. So we need these 2 sheets to stay around for longer. Okay. So if my pressure vessel only see normal stresses on any one section, another way that I can represent that is by drawing a stress cube and saying this is like my sigma X, like my sigma Y, And that's my stress cube. There are no shear stresses. So I can draw them in, but they're equal to 0. So don't have to. So I have my sigma y, which is what, 12.2 KSI. My sigma x, which is 6.1 KSI. My question was originally, the material making up this vessel fails in shear. So we find the maximum shear stress acting on it, which ironically we just said is 0, but that's the sections that we've drawn. We start to rotate this stress cube, we're going to start seeing shear stresses pop by, and that's something that we've seen from like back in Moore's circle days. So that's exactly what we're going to do. We're going to draw Moore's circle for this. So I know that I can find the center of Moore's circle by finding kind of an average stress. That's like a sigma x plus sigma y over 2. So this is the center of Moore's circle. So add those. Oops. Those by 2. So it's like 9.2 KSI. Cool. The radius of Moore's circle said is what? X minus sigma y over 2 squared plus tau xy squared. I already said that this is 0, goes away. So sigma x minus sigma y, 6.1, 12.2 minus over 2 squared, square rooted. That gets you 3.1 KSI. That's a 3.1 KSI. Sorry, I draw the KSI really super small. Okay, so we have a center and we have a radius. We can draw a circle because that's geometrically, that's all you need to draw a circle, right? You need a center point and you need a radius. So we have that. So let's get drawn. So I'm gonna come over to here. And please stop me at any time if like you need me to slow down or work through something ahead. So if my axes for circles have my normal stress axis and my shear stress axis, well, I'm the center of my circle, what, 9.2 KSI. The radius of my circle was 3.1, so probably about the right amount. So 3.1 KSI this way would bring me to like 6.1 KSI. 3.1 KSI this way bring me to like 12.2 KSI, right? And I could draw myself a kind of crappy looking circle. Woo! There is the circle of Moore. I can outline it a little bit. So there's our 2D Moore's circle. Great. Any questions on that first one? All right. So when we did all these computations before, we knew that there's no forces coming out of the page here. Like sigma z was 0. So if I looked at this not just in 2D but in 3D, I could rotate this stress cube by 1. That'd be like sigma z. Let's look at this like sigma z and sigma x. So this is 0. This is 6.1 ksi, right? That's just from before. So I can go back through the same process that I just did, right? Sigma, called find a center for this circle now, and the radius of this circle, same as last time. So find the average stress, which in this would be like 3.05 ksi, and the radius of the circle, which would also be 3.05 ksi. I can go back to here and draw it, or I could just say, hey, here's one point on my circle, here's another point on my circle, let's go at it. But let's be thorough. So sigma average, sigma x plus sigma z over 2. So that's 3.05 ksi. And the radius by inspection is going to be the same thing. So I can go over to my plot. I can say, okay, here's the center of that circle. And there's the circle itself. And that's kind of my, see, this is based on my stress cube that had x and z in it. This circle here was based on the stress cube that had x and y in it, right? So my last one's got to be based on the stress cube that has, on the stress cube that has z and y in it. So it's the one that I haven't done yet, if I'm thinking of like dimensions, right? Like x, y, and z. I have x, z, I have x, y. I haven't done z and y, right? So do that. Something that I know though is that this last circle, it has to connect everything together. So I almost don't have to do its own set of equations. Just say, well, I have a point over here on one end of my sigma axis, and all my circles have on the sigma axis, like all the centers are on the sigma axis. So know that if I find 2 points of the circle on the sigma axis, I can define the entire circle. So like I know I have one end of the circle there, because it has to connect from one end of the diagram to the other. The other point has to be here. That means that I have my diameter, right? In this case, my diameter is what? 12.2 ksi, because measuring from 0 to 12.2 ksi. And I can draw kind of my all-encompassing circle, which is the YZ circle. And the radius of that circle, if the diameter is 12.2 ksi, the radius has to be 6.1 ksi. And that, it's the highest point here, the highest point on this 3D Mohr circle, or on this 3D stress cube. So this is my max shear stress. And that's what I'm going to have to plan my material choices around. Are there any questions on this process? Need to ship coffee to yeah. Okay. Just take that as a guess, and I'll see if I can set up some coffee deliveries for Saturday. All right. So that's for thin wall pressure vessels. That's all. That's all the further that we're going to go there. All right. So you're all set to go. As far as buckling goes, don't worry. This will not be on your test. Let me say that one more time. Buckling will not be on your final exam. So what we just finished is the end of what could be on your final. Okay? This next thing that we're going to talk about, it's just something I want you to be aware of because it's kind of an interesting phenomenon, but it will not be on your final exam. Okay? So, buckling. Buckling is kind of an interesting phenomenon because say that we have this bar. This is my rubber bar of truth. So if I start to compress this bar, so right now I'm pushing the two ends toward each other. What would we expect to happen if I just compress this thing? What's going to happen? Is it just going to keep scrunching together like a spring? In theory, it should. However, if I keep pushing, you see how it starts to bend out there? Like it's not doing what our analysis said it should, right? It's developed this curve in it, and it hasn't failed. Like it comes back to its original shape. It hasn't yielded. So by all our definitions, this bar is still okay. I haven't passed its yield stress yet, but if I'm designing a structure, like having something that goes like that is probably a failure case. Like this probably counts as something not doing what I want it to do. It probably counts as something breaking. If a wall of my building did this, I'd count it as failed. So what is this? This is it's called it's a failure phenomenon that occurs before the yield stress of material. So it's something that's kind of important for us. So this phenomenon is called buckling. That's what it's called. That's what we've been calling this, and it occurs. You look back at how this thing failed, how it buckled. It's called, as soon as the middle of it kicks out, you see how it's going off to the side, like that. As soon as it starts to go, like it really wants to go, I can press a little bit, and I'm pressing the exact same amount, and it doesn't take. It's not hard for it to just kick out like that. So as soon as it starts to go, it just goes all at once. So we get into it that this failure has something to do with forces at the two ends not lining up anymore. We get into it that it's something to do with the middle kind of kicking out in one direction or another. And we can say that because if we remember back to our bend stress problems, that if I had something like this, if I had a thing like this, I'm pulling on each end. If I take a section up here, there's going to be a bending moment there because forces aren't in line with that section. So as soon as a section gets out of line with where I'm applying forces, there's going to be a bending moment. And the more that it's out of line, the greater the bending moment is. And we just finished a whole few weeks on how bending moments create deflection, right? So we can say that the more that this is bent, the greater the bending moment, and the more it wants to bend. So this is a dynamic phenomenon. It's also a self-perpetuating one. As soon as it starts, it wants to keep going, which is why it's called a mechanical instability. So a spring, like if I pull this apart, this is stable because as soon as I let go, it wants to spring back to its original shape. Like if I take a rubber band and I pull it, it always wants to come back. That's stable. It comes back to its original it wants to return to its original form. So that's a stable thing. Buckling is an unstable phenomenon. As soon as the rod starts to buckle, it wants to keep on going. It doesn't want to return to its original form. So this is an unstable phenomenon. And as bending is very dependent on its end conditions, buckling is very dependent on its end conditions. For example, if I force the two ends to be straight, it's going to be harder to buckle than if I let the two ends kind of do whatever. You can see how easy it bends when the two ends aren't forced to be straight, as opposed to when I force them to stay straight relative to one another. So there are a couple of things that we can kind of intuit about it. However, if we run out the math, which is saying if we look at beam in compression, if we say that if we want to know the smallest amount of force, or the critical amount of force, you might say, that is required in order to start a bend in the beam. Because as soon as the bend starts, like we said, it's going to keep going. So we want to know the minimum amount of force required to start a bend like that. And we'll say that's bending by some amount y. So you might say that the bending moment is going to be P crit times y, because that's the moment that's being made around that section. If we work out math, we'll find out that P crit pi squared pi over the original length of the beam squared. As this is highly dependent on what our boundary conditions are. So this for a case where the ends are pinned. In terms of like what the moment of inertia is, or the second moment of area, that it depends on the shape, right? So for a circle, it's equally likely that let's call like this rod's going to buckle this way or that way or that way or that way, right? Like if I press this together, go in any direction. It just matters where kind of the unbound occurs first, because it's a circle, right? And the properties are the same in every direction. If this is a I-beam, properties aren't the same. It's easier to bend an I-beam one way than another. So really, the value of I is whatever the minimum moment is for the cross section. So you can kind of predict what direction that it's going to fail in. As I said, the critical force also depends on kind of what your end condition is, whether or not they are fixed, they're pinned, if it's free, whatever. So the application expression will change. But in the grand scheme of things, I just wanted you to see something about buckling, because it's a failure mode that doesn't require force above your yield, stress above your yield stress in order to fail. So with that, that's all that I got for today. Keep in mind that on Wednesday, I'll be doing some review. So please send me problems that you want to look at prior to Wednesday if you have an idea, so that I can do review on stuff that you want to review. That is called, else I won't really have a whole lot to go on. And that's all. And that's all I got. Any questions?
So, bottom is this stuff we've been going over like on Friday and now today, that's not going to be on the final. You said.
I said everything prior to buckling is on the final.
Oh, so pressure vessels are on the final.
Correct. Pressure vessels, more circle, are on the final.
Okay.
Buckling is not.
Okay.
Correct.
All right. Oh, excuse me. Sounds good then. That's all my questions.
All right, thank you.
All right.
Brother Maurice, have a good one.
You too, Nick. See y'all.